Hello, viewers. In today's class, we are going to discuss yet another important and very conceptual problem from integral inequalities. Right? So, in this class, we'll prove this inequality. That is, we are given an integral I from 0 to 1 square root of x raised to 4 plus 2. And here we have to prove that the value of this integral I is greater than or equal to square root of 2 but less than or equal to square root of 3, right? So without actually evaluating this integral, we have to estimate the value of this integral I between these two numbers. So viewers, here we have to estimate this integral, and we have to show that the value of this integral lies between square root of 2 and square root of 3, right? And here we are not going to evaluate this integral. So we'll prove this inequality with the help of an important result from integrals, that is known as the mean value theorem for integrals, right? So the mean value theorem for integrals says that if we have a closed interval, say a comma b, right, and we are having a function, say y is equal to f of x, and this function is defined on this interval, and it is also continuous, right? So mean value theorem for integral says that the integral a to b f of x dx is equal to b minus a, that is the difference of upper limit and lower limit, multiplied f of alpha, right, where alpha is some number which lies between a and b, right? So this is the mean value theorem for integrals, and this is a very useful result for solving these kind of problems. So now if we compare this integral with this one, then we can see that the value of a is 0 and the value of b is 1, right? A is 0, b is equal to 1, and f of x is given by square root of x raised to 4 plus 2, right? So using this result, we can now write this integral I, that is 0 to 1 square root of x raised to 4 plus 2 dx is equal to b minus a, right? B is 1, a is 0, so we have 1 minus 0, and then multiplied with f of alpha, right? F of alpha, where alpha, this alpha is some number which lies between 0 and 1, right? So 1 minus 0 is simply 1, so we have 1 times f of alpha, that is equal to f of alpha, right? So our integral I is now equal to f of alpha, and f of x is equal to square root of x raised to 4 plus 2. So we can now write the value of f of alpha by simply replacing this x by alpha, right? So we have I is equal to square root of alpha raised to 4 plus 2. So now our I is equal to this quantity, that is square root of alpha raised to 4 plus 2, right? And now see, here we have this inequality, that is alpha lies between 0 and 1, right? So what we will do, let us take the fourth power of all the terms in this inequality, right? So raising these three terms to the power of 4, we have 0 here, then we have alpha raised to 4, and here we have 1 raised to 4. So this is 0, this is alpha raised to 4, this is 1, right? Now see, here we have alpha raised to 4 plus 2. So what we will do, let us add 2 throughout this inequality. So we have 0 plus 2, alpha raised to 4 plus 2. Here we have 1 plus 2. So this is 0 plus 2 is 2. This is alpha raised to 4 plus 2. This is 1 plus 2, 3. Right? Now, here we have square root of alpha raised to 4 plus 2. So let us take the square root of all these three numbers. Right? So we have square root of 2, square root of alpha raised to 4 plus 2, and here we have square root of 3. Right? Now square root of alpha raised to 4 plus 2 is I. So we have square root of 2 I, and here we have square root of 3. And this is our desired inequality. So this inequality suggests that the value of this integral I, it lies between square root of 2 and square root of 3. So this is how, by making use of the mean value theorem for integrals, we can solve these kind of problems related to integral inequalities.